Good morning. My name is Vishnuvardhan. I'm from Electrical and Electronics Engineering. My EPTS Tech Talk topic is mechanical distortion of ACSR conductor due to forest fire. Distortion of aluminum stranded conductor steels re, reinformed reinformed in transmission and distribution power lines would be slowly progressed by various factors such as materials, components, manufacture methods, and installed environment. ACSR shows more complex corrosion mechanism than any other power lines of aluminum or copper conductors, since it consists of galvanized steel strand and aluminum strand. In general, overhead power lines may be attacked by atmospheric corrosion as well as galvanic corrosion, grease or fatigue corrosion. In addition to natural distortion or corrosion of conductors for a long period of time, forest fires sometimes would produce serious troubles in maintaining the stability of overhead power lines. Forest fires are usually accompanied by high temperature, humidity, smoke, dust, and flame. Furthermore, they may often cause a short circuit between conductors. Therefore, transmission conductors installed on mountains often would have trouble in keeping the power equipment stable. After putting out fires, the tension load of conductor may be remarkably reduced so that any assessment can be made for those conductors whether they still would be used or be replaced sometime later. However, However, there have not been any trials for inspection such results caused by forest fire. Most power companies worldwide have established different refurbishment criteria which are usually determined by the elapsed years of conductor load rate, line status, and the power utility. Other method is to test several mechanical or electrical performance of jumper wires removed from the line. Therefore, aged overhead lines in service may be often refurbished by the managers' decision through the results obtained by line inspectors. There is no criterion for refurbishing line conductors degraded by forest fire. In practice, the end life of power lines should be directly determined by the tension loss of conductors. Hence, to determine the mechanical or electrical stability of the line, the tension load of all power lines may be preciously tested. This seems to be impossible, even though any realistic techniques may be applied. Therefore, another method should be developed to estimate the distortion degree or the tension loss of power lines in service without removing the overall spans or cutting off jumpers. Several corrosion phenomena are discussed here regarding the overhead power lines degraded by forest fires through several experimental tests and analysis. Mechanical and material performances for artificial fire test samples are also presented. Distortion of ACSR. Distortion of ACSR shows a general ACSR conductor which consists of hot dip galvanized steel strands in inner layer and hard drawn aluminum conductor in the outer layer. Aluminum strands Aluminum strands are used as conductors while steel strands are used to withstand most of the tension loads of power line. The surface of the steel strand is galvanized in order to moderate both atmospheric and galvanic corrosion. The galvanizing layer has iron zinc alloy. The depths of both zinc coating and iron zinc alloys are approximately 20 meters. Galvanized steel stands a new stand zinc loss rust on the surface particle galvanized corrosion. Aluminum stands in the outer layer of ACSR are directly exposed to the atmosphere. Even though aluminum is an active metal with a high affinity to oxygen, it has a high corrosion resistance in the air because the film oxide performed on its surface protects the aluminum stands. At the initial stage when ACSR is exposed to the atmosphere, Aluminum strands began to corrode rapidly. However, its corrosion rate decreases with time since aluminum is usually highly resistant to corrosion. The galvanizing layer on the steel strand surface moderates the rate of corrosion as it may be directly exposed to the air or humidity and it has strong chemical affinity with oxide ions. Overhead ACSR conductors have a good condition to penetrate humidity or water into the stands. In addition, dust or pollutants together with humidity in the atmosphere would form electrolytes, so the corrosion rate of the zinc layer becomes high. After the zinc layer becomes corroded, as shown in figure, aluminum strands in the inner layer are be directed contact with the bare steel strands and they could be attacked by the galvanic corrosion. Hence, the electrical resistance of the conductor would be great increased and this portion of conductor would be overheated. Finally, conductor distortion would rapidly progress and its mechanical strength would be much reduced. Such local corrosion may often lead to failure of power lines, characterized by a non-linear coupling. We may have an incomplete knowledge of forest media properties and initial conditions of forest fire propagation. Moreover, several probability factors make it difficult to perform a forest fire test. However, it may be possible to find results of material variations after conductors are blazed. It is desirable to use a suitable method to analyze the material performance transmission lines due to forest fire. One is to estimate tension load reduction or electrical behavior based on analyzing the material and mechanical data for various conductors collected from the field after putting out forest fire. However, no research data is available and not enough samples of blazed conductors. Therefore, we primarily try to prepare several conductors under testing by artificial flame similar to real forest fires. First, both new and aged ACSR 480 samples were heated by using a gas burner for a 3-minute interval. Then they were slowly cooled in ambient temperature. All real forest fires always carry humidity, smoke, and dust. However, such factors would not be considered in the experiment since any exact modeling for forest fire could not be specified before experimenting. ACSR for 480 consists of three aluminum layers which have 25, 16, and 9 stands respectively, one galvanized steel core, and six steel layers. For each layer, three stands are tested to obtain tension load and to examine microscopic phenomena and material components. An aged conductor and an sample for a 9-minute heating. The aged aluminum stand shows aluminum oxide and some cracks on the surface. However, the surface of the blazed stand have more cracks. It can be easily concluded that such conductors would corrode rapidly after blazing. Although a few strands have mainly pure aluminum and aluminum oxide layer is formed on the surface of blazed conductor which includes minor components such as silicon, sulfur, furous and zinc beside air. It is obvious that a part of degradation components would appear on the surface of the aluminum layer while the galvanized steel strands in the inner layer is degraded by glaze. Finally, the effective cross-sectional area of the aluminum would be reduced due to fire heating and the electrical properties would be also degraded to some extent. A new galvanized steel strand consists approximately 20 to 30 pure zinc layer and the 20 zinc alloy which is mainly Zn and a little of zinc oxide for a blazed galvanized and a pure zinc copper layer with a new strand shows a double increase in the depth. This is due to oxidation of pure zinc with oxygen in it. Further, high temperature may melt a small amount of aluminum the interior strand. A part of oxidized zinc would break away from the steel strand to the outer aluminum layer. Mechanical distortion. it may be assumed in general that most metals would show less mechanical strength after being exposed to heating flames with high temperature. As mentioned above, fire flames are in direct contact with the conductor surface, so that aluminum strands in the outer layer would lose their tension loads more than the other layer. In order to estimate any distortion of bladed ACSR's conductors, some relations between ultimate tension load, extension rate, and fire duration should be determined. Thank you.